Okay, welcome everyone. My name is John Reynolds. I'm a product manager at Aleo. Today we have a very exciting talk with AMD and VMXL, and excited to go through some of the conversations related to hardware and the opportunities that we have to speed up some of these different compute as it relates to ZKPs, and maybe talk on some of the different compute environments. So, Alex is going to join us as well. So, yeah.
Sorry to be late.
I'll open the floor. I know Alex has introduced himself already, but I'll let both of them introduce themselves, and then we can start to get into it. You can go ahead, yeah.
Matt Fields, CEO of VMXL. We are infrastructure as a service, platform as a service for AI acceleration, so out of Cheyenne, Wyoming, and elsewhere.
Perfect. Hamid?
I'm Hamid. Does this work? Yeah. Director of product at AMD's Adaptive and Embedded Computing Group, kind of a mouthful, and happy to be here.
Okay, before we dig in a little bit more, I'd love, Hamid, to hear a little bit more about like some of the areas of hardware that you focus on. Today we'll talk a little bit about a variety of different compute environments, from CPU to GPU, FPGA, and then ASICs. I know AMD has a lot of experience in a variety of those compute environments, and VMXL has also been a close technology provider for zPrize. zPrize is an effort to help accelerate the compute of zero-knowledge proofs in a variety of different parts of the tech stack. We focused on hardware. This year we're working more closely on end-to-end proof generation, but both of these teams have helped support that effort and provide different resources to improve it. So Hamid, I'll let you go into a little bit more some of the compute environment that you focus on, and then Matt, I'll let you follow up.
Sure. So AMD traditionally has been involved with the blockchain community, I would say, for 5-10 years. And in the last couple of years, we have shifted toward infrastructure, supporting the blockchain infrastructure, and how we can address some of the scalability, privacy, security challenges that blockchain network faces using hardware acceleration. And specifically, my team has focused on the FPGA. So obviously, we have the GPU team as well that they have been involved as well. As far as zPrize is involved, we have been a technology sponsor in 2022 and 2022 and 2023, 2024. And we are looking forward to continue that engagement. Initially, when we started, I guess our involvement was through one of the partners that work with zPrize and introduced us. And then we got to know Alex and John and the team. And ever since, we have been a supporter of the community and looking forward to continue the engagement.
Thank you, Hamid. Matt, if you want to speak a little bit more in terms of your level of support for zPrize and then some of the things that you focus on in this space.
Yeah, definitely. So in terms of the zPrize, our background is very heavily in FPGAs, working with the programmable solution group at AMD and also a few other ones. But mostly with the zPrize, we were very interested in decentralization and kind of being able to move different initiatives forward in the blockchain. What we are working on right now is the U250 with AMD and the zPrize, enabling that, mostly because of the memory and the capacity on it. What was the other part of it?
I think that covers it well. Yeah, just talking through some of the focus points of the hardware solutions and the support systems for zPrize.
Cool. We've also worked on, in terms of data centers and stuff like that, related to the enabling the hardware. We work worldwide with enabling the infrastructure solutions and the platform to enable these different, whether it's AI acceleration or blockchain-related activities. So that's kind of our bread and butter, is enabling the hardware, abstracting that. I think you spoke about it at the first part about getting the infrastructure out there, where everyone's kind of centralized right now, and moving that away. That's kind of our what we're trying to push for and move towards, is decentralized infrastructure to enable everyone else in what you're doing out there. So.
Great, thank you both so much. So we'll dive into a little bit more of the specifics now of zero-knowledge proofs and how some of these compute environments can support enhancing them, making them more efficient, and reducing the amount of time it takes to generate those. Hamid and, Alex also, just to put out there, Alex is actually the original founder of zPrize, so he's a great person to have on the panel as well to speak to some of his considerations to how we can improve the open source nature of zero-knowledge proof generation and the efficiency of it. So, Hamid, I'll start with you. What specific processor features enhance zero-knowledge proofs, ZK snarks or ZK starks, from the computation side?
Sure, but before I kind of answer that question, I want to just say a word about Alex. Definitely, the work he has done has been remarkable in terms of advancing, the access to the body of work that different researchers have created through zPrize. As a matter of fact, anywhere I go, people come to me and say, we want to get started. And where we start, how do we get started? We want to do, accelerate a primitive or, create, faster, generate proofs faster. And, what's the starting point? And always I say zPrize, there is this body of work that exists and it's all open source. And definitely, I think that contribution hasn't gone unnoticed for sure.
And I think some people in this room have contributed to that body of work. So thank you, because this is not possible without, the efforts of the broader community. So, yeah.
So now, great. So now, in terms of, different type of hardware that is used for ZKP acceleration. So when we started, and I guess in 2022, the initial focus was, see what primitives are used, what cryptographic primitives are used to create the proof system, and then how can we make those primitives faster? So, a lot of focus on accelerating MSMs, multi-scalar multiplication, entity number theoretical transforms. And then you look at some of those primitives that are part of the proof. People said, okay, MSM, for example, you can do bucketing and you can really do massive parallel calculations. And, let's use GPUs and FPGAs, and same thing for NTT. Obviously, NTT is a little bit more complex in terms of how you calculate the large polynomials, and then you have to go access data from the memory back and forth, a little bit more unstructured. So FPGAs might play a little bit better there. So the idea was, let's try this on different GPUs, FPGAs. Obviously, we started with some of our we had a card called C1100, which was we called it an FPGA acceleration card, and that's what we used for zPrize 2022 / 2023, I guess. And then this year, partnering with VMXL, we have used the much more powerful FPGAs to accelerate some of those primitives. But kind of going beyond that, if you are really thinking about creating a proof system and accelerating that, you have to think about what are all the components that goes inside that proof. So you might have some MSM and you might have some entity, and depending on what type of proof system you're using, what type of polynomial commitment scheme you're using, is it more Fry-based? Is it more with a ZKP? And depending on what you're using, then maybe use one type of hardware versus another. But one thing we noticed, kind of getting into this journey a little bit, is you really have to think about your overall system, because they say 80% of your system or 90% of your system is going to be MSM and NTT, and depending on what proof system you have, it might be, the portions might be different, but people kind of tend to ignore that 10% or 20% fluff, and that ends up becoming extremely important, because even if you accelerate the MSM piece and NTT piece, to zero, basically. You eliminate the whole thing. If you have 10% fluff or 20% fluff, so that means that at most you can accelerate 5 to 10 times, which frankly is not going to be nearly enough to answer a lot of practical applications. And if you want to accelerate your solution 100 times, 1,000 times, then you have to think about whole application acceleration and how you can create a solution that addresses all the components of a proof system versus a specific cryptographic primitives. And then in that vein, you have to kind of start thinking a little bit broadly versus, FPGA is better, what FPGA is better, what GPU is better. You have to think a little bit more heterogeneous and say how you can use all these compute engines connected together to accelerate the totality of the proof system. And we see a lot of work now. People are trying to implement some of these to really accelerate the overall proofing system. I went a little bit too long.
No. Has anyone heard of Amdahl's law? So yeah, it's basically like, you accelerate one piece of a complicated system, then some other piece becomes the bottleneck, right? And I think that's very much what we've observed here, because, generating a zero-knowledge proof, which, by the way, is only half of, a zero-knowledge cryptography. There's also verification, right? And so that has many components, and each of which you can focus on, and beyond a certain point, that ceases to be the bottleneck. And so it's a very complex and evolving problem, and it also very much depends on the context in which you expect the proofs to be generated or verified. So a lot of interesting directions for future work and research.
Matt, do you have anything that you'd like to add?
I think I'd agree with both Hamid and Alex about the heterogeneous nature of acceleration as we're moving forward. It's becoming more and more apparent that you can't just use a single acceleration source, GPUs, as a kind of like a sledgehammer to all the problems. It doesn't work well with nails, doesn't work well with glass or anything else. You've got to change that up, and this is really where it's going to, is getting all of these pieces of hardware together and enabling it as a whole solution and moving that forward.
Okay, going off of that, I guess a little bit, like so we've mentioned a lot of different hardware solutions, and we're talking about trying to kind of think of how we can leverage each one in different ways. But from your experience so far, I'd love to hear what leading technologies in the hardware stack do you think are the most effective for some of these different ZK proof systems?
Sure. So the first talk, Alex mentioned something that was very interesting and said, when you think about creating a system or a solution, think about the end use. And really, the end use is going to dictate what hardware stack you are going to use. Even you might not even need acceleration, right? Maybe the thing running on a CPU might just be good enough, right? Or you say, okay, for my end use, what's the bottleneck? Say, for example, if you are thinking about some interoperability, and we made an announcement with Wormhole a couple of days ago. If you are thinking about like interchain interoperability, then latency is extremely important. So then you have to say, okay, what kind of hardware proof system is going to enable to give me the lowest latency possible? Then maybe you look at some of the FPGA type solutions, because for latency sensitive applications, the FPGAs have performed extremely well. And then maybe you are thinking of a solution that you are really focused on throughput. You want to create as many proof as possible for the end use. Maybe you have some type of roll-up application. And then the system you're using is very MSM heavy. And then maybe you lean toward, GPUs. Or maybe, as I said, you might create a more heterogeneous system. So really, you have to start. The starting point has to be start from the end user, understand what type of experience you want to develop, you want to create and deliver to your end user, and then based on that, figure out what kind of hardware stack is going to be able to address those needs, right? And I see that a lot of startups, a lot of super smart engineers, and they want to develop something and faster, but really you have to step back and see why I'm doing what I'm doing.
Yeah, and I think, but there's also at the level of the different platforms, support for example, different instruction sets, or integration of new and different types of hardware inside of like mobile, for example, I think can make a huge difference. In fact, this year for the Z Prize that we're currently running, so we ran in the last 2 years, we've done a competition around accelerating MSM, which has been a big part of most of the Snark-based systems, in a WASM, which WASM is kind of the runtime environment that you run in your browser. And actually just recently, WASM integrated support, or now enabled support for SIMD instructions, right? And that actually it unlocked a whole bunch of new acceleration opportunities, right? So in addition to the physical hardware itself getting better, at the level of number of transistors per nanometer or whatever, now you also have just the platforms that, back to the use case thing, it's like everyone has a mobile phone, or most people use browsers that support WASM. So now you can actually unlock more acceleration than you would have otherwise been able to previously. So it's very dynamic, I would say.
Yeah, okay. Well, speaking of dynamic, I think one of the things we've also noticed with Z Prize is there's actually a lot of scope for software improvements to enhance the way that the hardware is being used in order to see a lot of improvements in efficiency and in acceleration. And as a result, I guess a question from that might be, are we at a point where we're ready for ASICs in the ZK space? Or should we be relying on existing hardware solutions and trying to refine those before we get to a place where we start leaning towards ASICs?
Actually, I get that question pretty much everywhere I go. And there is no really simple answer to that. One thing I tell to a lot of startups is what you imagine how hard it is to create an ASIC, it's way harder. So do not underestimate how difficult it is to actually create a silicon you can take to production. Even for AMD, and AMD, and obviously we came from Xilinx side before we got acquired by AMD. 20-year history of developing silicon, and even one piece of silicon going to production, you see the challenges, not just in the design process, not even just in the tape-out process, when you get the silicon back and you want to do validation on it, and then you have to iterate on it, and every mistake is multi-million-dollar mistakes. So you have to really think carefully before you kind of venture into that area. Now, that said, at some point, like what happened for HTTPS, every CPU has a little bit of an encryption engine now in them, and it's very trivial. We are going to get there at some point, but I think, which is great, by the way, because a lot of young people are really want to innovate and create their own chip and all of that. But I would caution people, generally speaking, the way to think about it is, frankly speaking, for any IP that can be implemented on an ASIC, it can also be implemented on an FPGA. If you think about what you're compromising, the price you pay for doing something on an FPGA is you're going to spend approximately 10 times the silicon area. So if you have some form of IP, some form of logic, and you can create an ASIC, and that ASIC is going to be a square millimeter, the same thing on an FPGA is going to be 10 square millimeter. That means the device, per device, you are going to pay more for it. But the advantage is there is no tape out needed. You have to program it still at the gate level, but you take a device off the shelf. And my view is, versus instead of jumping to creating an ASIC, think about again the end user, where you are going to deploy your solution, and create that, deploy it after you have product market fit, after you have some level of deployment, and you see, okay, the use case is validated, then you can go and raise significant amount of money and venture into that world. But jumping into that before you have validated that something actually is going to work, in my humble opinion, is a little bit premature. But if you have a ton of money and patience and investors with deep pocket, have at it.
Well, and I think it's important to note too that like ASIC, I think sometimes people misunderstand what application specific means, right? Like think about Bitcoin ASICs. Like a Bitcoin ASIC does SHA-256 hashing, and that is all it does. It's not a hashing ASIC. It does one hash function, right? And you think about these, like a zero knowledge proof is a much, much more complicated algorithm than just a SHA-256 hash, right? And so there's a lot of components to it. And then there's different cryptographic assumptions which drive different types of algorithms that feed into zero knowledge proofs. And then, there's different emphasis on, NTT or MSM. Like there's a range of options, and it's pretty hard in my view. I mean, even if you ask many people in the space, that sometimes I think sometimes it's a little bit of a thing that people like to say is like, oh, we're gonna have a ZK ASIC, but it's like just drilling down into specifically what is the thing that's being put on silicon. I think when you push most people, they're like, well, we're going to get like an NTT ASIC or an MSM ASIC, and that's usually what you end up with. And so I think to Hamid's point, and actually maybe I'll just say it even more strongly, you need a market. You need a real market where that's hundreds of millions of dollars to justify going from a 10 millimeter FPGA to a 1 millimeter ASIC. That's what I think gets you there.
And one other thing I want to demystify, I know we only have 5 minutes. So I hear people say they want to create a programmable ASIC, which is a little bit of an oxymoron.
It's called an FPGA.
So basically, and you can have a bunch of registers, and maybe you can have a little bit of but at the end of the day, you are going to just create a less efficient ASIC. And either that thing is going to work, which somebody is going to come and build a really more efficient ASIC, or it's not going to work, and still your tens of millions of dollars are kind of down the drain. So again, I really caution people to be careful venturing in that world.
I would add a little bit more to that too. So when you look at an ASIC, it's really good at doing something really, really fast. But when you look at the market and how it's moving with ZK especially, if you create something right now, by the time you get it produced, it's taped out, and it's actually created, it's already too late. It's already too slow. Yeah. And like Alex mentioned, it's also that we're doing more things than just one. So in that sense, an FPGA lock makes a lot more sense. You can meet with the market. You can change as the market changes. And as the encryption or algorithms change, that also makes it much more usable. Now, later on, after things have more solidified, just like your vehicle, your braking system or anything else, if you want to throw an ASIC at that where it can process it really fast, it doesn't change much, it's going to do the same thing over and over, that's a place for an ASIC. And there's certain use cases that you would make use of an ASIC for, but in FPGA right now, this is really the programmable solution that we need. And it's a fine-tuned hammer that you can use for whatever solution is going to be.
But I think, and also taking that in the inverse, so we kind of say, okay, why not ASIC? But I think why FPGA and GPU is, I think I also want to call out that, like, to get to the market for a ZK ASIC, you need people to see the use case. And sometimes it's like a chicken and egg problem, right? Like if the use case for like identity, like a zero knowledge proof powered identity protocol, like that kind of is only practical today, frankly, with some specialized hardware. So you kind of, to show that, you need to have some acceleration, right? So it's not sufficient to just do it on my laptop, right? So you need an FPGA or GPU, depending on the use case.
Yeah, exactly. Like think of it a black box. So your
Exactly.
black box is going to cost $10,000 to build. Who cares? When you go to mass and you prove product market fit, you can do an ASIC and the box is going to cost $500.
Exactly. But it is like, this was really the key. I think that the Z Prize, and particularly like the focus for hardware acceleration at this stage, in my view of the industry, is to prove that these applications that people are interested in can be done. And then to get people excited about, okay, well, this actually has real utility, and then get the flywheel going that then will ultimately lead to an ASIC.
Exactly. Yeah, great point. Yeah.
All right, well, I will let us wrap it up there unless anyone has any final closing remarks that they want to add in.
I have a question for John, who is a product, it seems, of the Aleo Foundation. Yeah, so based on the label there, but no, John's a product manager at the Aleo Foundation. But what's been your experience managing Z Prize 2023, 2024? What are you most excited about?
What I love about Z Prize is the community coming together. I think it's one of these unique areas where, because we're focused on open sourcing the outcomes, we can get a lot of very smart people working on a lot of these challenges that are quite complex and hard to come up with a solution to. And all of the contributions work together to make a library of this open source content that we've seen used across the ecosystem in a variety of different ways, and people are very excited about what has been produced. And so for me, continuing to see the percentages of improvement and 10x in the speed and the efficiency of proof generation, it's cool to be a part of that and to help organize the teams who are bringing that to life.
One thing I want to add also is for next year, we definitely are going to have more interesting hardware to share with the community. So definitely exciting things to come.
Stay tuned.
Thanks, everyone.